A21 damped harmonic oscillator. We learned the harmonic oscillator that is f equals minus kx, and f is always mx double dot according to Newton's second law of motion. This is a restoring force, spring constant, and x is the displacement from the equilibrium position where the spring force vanishes. If there is a damping force in addition that is opposite to the velocity with some coefficient, positive coefficient, the damping coefficient. In that case, the linear differential equation, the second order linear differential equation becomes the equation of motion. As we learned yesterday, this equation can be reduced into a very simple form that is consistent with mass spring system. However, because of the subtraction due to the translation of the origin, what we have may have a coefficient that can be either positive or negative, or even it can be zero. So we have the three kinds of cases to solve the equation. But anyway, first, let us return to the original problem and consider the general discussion. Find the differential operator D. Okay, this one can be thought as a result of application of a differential operator to x. So how can I write this operator? I have mass, second order time derivative, b times the first order time derivative, and k. Okay, in mathematics, they don't teach you the dimensions of physics, but in reality, all of the variable has a physical dimensions. It is different from mathematical question, so we have to be very careful about the addition of these sometimes number, sometimes operator. One can add mathematical objects all together. In mathematics, they don't care because always they consider number only. In here, mass, this is a coefficient of the damping force, the spring constant. These three terms can be added only if the physical dimensions of the three are the same. For example, 1 centimeter plus 1 kilogram cannot be added. But in mathematics textbook, they don't tell you about this. Just 1 plus 1 is 2. But stupid student may think 1 centimeter plus 1 kilogram is a 2 and ask me a question, how can I say it? Is it 2 centimeter or 2 kilogram? Nonsense, because they are ignorant of the physics. So if you learn only mathematics, this kind of thing really happens frequently. So be careful. The physical dimensions of the three must be the same. Okay? Determine the dimensions of B over M and K over M. Because these three objects are of the same dimensions, why don't we consider this? So we multiply the reciprocal of mass to this identity, then it becomes the time derivative operator twice, and the first order time derivative, and then d over m. The third one is k over m. We know time has the dimension of time, and 1 over t is 1 over t. What's the change in time? Change in time that also has this dimension. 1 over change in time, the same dimension. Therefore, derivative, each derivative, this derivative operator has a time reciprocal. And second order time derivative, 1 over t squared. As a result, I can determine this one is same as this. Okay? And if I take the square root k over m, 1 over time. Similarly, if I cancel this one single power, then b over m is again 1 over time. So square root of k over m and b over m, these two coefficients are of the same physical dimensions, and the usual unit is hertz. So 1 second reciprocal of a second is hertz. Consider the equation of motion for a damped harmonic oscillator. We learned that this one can be simplified into a very elementary second order differential equation if I factor out this exponential factor. You recall that only if this parameter is determined by b over 2m, but for example, if you were solving a different problem, but with the same coefficients, your answer of to this quadratic equation has a factor b. If you have this b over 2a, that is the central value, and you have plus minus square root something, right? Quadratic equation solutions. So completing the square is determining this exponential parameter of the exponentially decaying factor. That is a very, very important. And then you are left with this simpler differential equation. Let's see. First, this is a real number, right? So any real number can be positive, can be negative, or zero. Real number is always classified into order and positive, negative, and zero. What about the simplest case? Zero. High school student can solve this problem. The answer is this. Okay? And you don't forget the constraint. They are the same. So we learned this has the 1 over time scale. This one has 1 over time scale. Factor of 2 appears because of the completing the square. So in that case, it is a linear function. So after substituting this linear function into y, what you have is this exponentially decaying function multiplied by a linear function. And actually, linear function is slowly growing up, and exponential function decays arbitrarily small. Therefore, in here, for example, for simplicity, let me kill this. That if I have this term only, in that case, I have an x time axis and value of x. What's happening is, at the origin, it regardless of this value, actually it hits this intercept is 1 for the exponentially decaying function, and this one rises up. Product of this is because this one vanishes, absolutely 0. So final result is something like that. There's a bump and decays exponentially. So this is called the critically damped motion. It is not easy to observe in nature, the very tiny parametric space. However, it really exists. And in general, the solution is a linear combination is of 1 and t sum, and then you need to multiply the exponentially decaying factor that comes from the translation to kill the linear term by completing the square. Next, we consider overdamped motion. What is overdamped motion? It is the case when this parameter B that is related to the damping force is very large in comparison with the spring constant. Spring constant determines the force, restoring force. This damping force is the rate of decreasing the velocity to reach 0, the absolute value of the velocity to reach 0. So damping is very strong. Then, just like what everybody uses, the door stopper, door knob, and on top of the door, there is some spring in it, and you have a lot of oil to increase the damping force. When you open the door and do not want to slam the door, it automatically kills the velocity to reach 0 slowly, slowly, slowly. That is the overdamped motion. In that case, whatever value it may be, if it is greater, then your answer is a double derivative is proportional to positive number and itself. Aha! It is nothing but the exponential function with the scaling factor of this. Okay, the solution must be square root of this, square root of this, and plus minus, because second order derivative e to the lambda t will give first order derivative is lambda, and second order derivative one more time you have lambda square, and lambda square is a positive number. The solution is plus minus something. So lambda square equals 1. It is that lambda equals plus minus 1. So that scaling factor is multiplied to plus minus 1. That what is that? That is a square root something. And that is a positive. That we call overdamped motion. We already have exponentially decaying factor, and we have a linear combination of these two contributions. However, let's see what's bigger, b over 2m and square root of b over 2m squared subtracted by k over m. What's bigger? Positive, positive. This one is bigger. Therefore, even if there is a positive exponential contribution, multiplication of these two factors still decays as t goes to infinity. Sure, it decays slowly rather than this guy. This guy both negative, so it decays very fast. So these two contributions construct all possible value of the solution. So this is the most general solution for over-damped motion. So I need to delete this. Over-damped motion is wrong. Over-damped motion. The third one is a really interesting one we experience mostly is the under-damped motion. You have a pendulum and let it oscillate, but as time goes by, it will stop. So because of this exponential factor, and why is it oscillating? It oscillates because in that case, the spring constant is strong enough to win the game against the damping force. In that case, this part becomes a positive. I have moved that term from the right-hand side to left-hand side. And if it is a positive, it reduces to something like y dot double dot plus y equals 0. If I absorb this factor into y. So the solution of this is related to the quadratic equation that has y squared equals minus 1. Y squared y minus 1 solution is a plus minus I. And this solution determines the solution of the second order differential equation that is exponential function e to the I something, e to the minus I something. And we already learned that exponential I theta, Euler told us it is cosine theta plus sine theta, and plus minus exponential I something is equivalent to cosine and sine's linear combination. So eventually the solution is the same as a harmonic oscillator, but it does not have the original oscillating frequency. Instead, the frequency has been shifted by this due to the completing the square. That's the reason why we had to study in middle school, working hard, not simply remembering the formulas, never knowing the reason why we are doing something. Only physicists tell you why you should solve this problem. I'm not a mathematician, I'm a physicist. And you must learn that to solve your own problem you will encounter in future, then nobody will tell you the solution. You must construct your own solution after constructing your own equation of your life.